Hello, I think we're ready to go. Can you hear me?
Yeah.
Yes.
Okay. I think people are still joining the class. You should see my desktop and you should be able to hear me. And people are still okay joining the class. Okay, so this is the CS316 Programming Languages course. Uh, this is the website for the course. Everything we need for the course is going to be on the website. I don't use Brightspace that much. Brightspace is mostly going to be used for submitting your homework assignments. So all the content of the course is going to be here on the course website rather than on Brightspace itself. Okay, so there's a link from Brightspace to this course website. Also, if you just Google my name, like if you're on a cell phone or something, if you Google my name, it's almost always the top link will be a link to this website. Okay, so you can get to it either by going to Brightspace and then clicking on the link to the website from Brightspace, or just Googling my name. Okay, and first, what we're going to do today is go over the syllabus of the course and then start talking about some introductory material. Um, right now, you might have noticed that there's a link to says that there's a homework assignment up there. It's not up there yet. Okay, so the homework assignment is not quite ready yet. I hope it'll be up there later today. So we're going to go over the content of the syllabus and stuff. I just want to point out that even though there says see the homework assignment page on the website, the homework assignment isn't quite ready yet. Okay, so the website for the class has the course syllabus. So here's the syllabus for the course. Um, Here's a link to the textbook that we're going to use. The, uh, the the textbook has a couple different websites. This is where you can get a digital copy of the textbook for $30. Okay, so you can purchase a digital copy of the book from here. You can also go directly to the pub. It seems that the digital copy is being sold by somebody called Red Shelf, and then there's the publisher of the textbook. They're selling it. It's $77, and this is an actual paperback copy of the book. And then there's Amazon too, also sells the book. Okay, so the cheapest way to get the book would be to get this online version of it. Okay, and we're not going to use the book right away. I'll tell you in a minute. We're going to start off with doing some data structure stuff because we need to. There's a little bit more data structures we need for this course than probably what covered in the data structures course. So we're going to start the semester with some stuff about reviewing some things about data structures. Okay, so on the syllabus, this link here is to the online, purchase an online copy of the book. This link here is the actual website of the book where the author has PowerPoints that you can download like this chapter 1 is not the chapter of the book. This is just a PowerPoint about, this summarizes the chapter 1. So he has good PowerPoints. These are really good summaries of the chapters of the book. And then this third link is to the publisher where you can actually, if you wanted to buy a physical copy of the book, you can buy the book physically, a paperback copy of it. Probably the best thing to do is to get the online version. That's the cheapest version. Okay. All right. So that's the textbook we're going to be using, but we're not going to need it at the first week or so because we're going to start. We're going to start talking about some data structures things. Okay. Now the course is going to be mostly programming assignments. Okay, so you can have probably about six programming assignments through the course of the semester, and there'll be an exam near the end of the semester. And I realized last night I put here that the final exam, the exam will be at the end of the semester during final exam week, but I'm going to have to change that because then after I put that up there, I realized that um, I'm not going to be able to grade. I'm going to have so many exams to grade during final exam week that I will not be able to grade them. So I'm going to move that up a couple weeks before final exam week. So I'll have to come up with a date, but I'm going to change this date because I can't have all the exams during final exam week for all the classes I'm teaching, because then I'll have more exams than I could possibly grade in a few days. So this one exam will probably end up being towards the end of April. Okay, so it'll probably be towards the end of April. Okay, so I'll update this. I'll pick a date and I'll put a link. I'll put an announcement up there when the exam's going to be. Okay, so there'll be a bunch of programming assignments and one exam. Okay, and the exam will be near the end of the semester. Okay, and then the programming assignments. If you've had classes with me, you've seen how the programming assignments work. There's going to be a page describing each homework assignment. There'll be a zip file that comes with it. That's kind of described here. Okay, there's a page here that has up on the course website. Here's the page that describes. That'll list the homework assignments, and when a homework assignment is ready, there'll be a link to it, but it's not ready yet. Okay. When you're ready to turn in your assignment, here's a page that describes the instructions for submitting a homework assignment. We will be using Brightspace for that purpose. So when it comes time for you to submit a homework assignment, you want to read this. No point, there's not much use reading it right now. So the assignment will be due in a couple of weeks. When you're ready to submit the homework assignment, you might want to read this, okay? And when we get, when the homework assignment is actually up there, we'll talk more about it. So when the homework assignment, probably on Thursday, we'll say more about the programming assignment, okay? So the course website has the syllabus, the homework assignments, and the other thing on the course website that's real important is this link here, lectures and readings. For every day we meet, there'll be an entry in this page for that day. So, this is the entry for today. It starts with a link to the Zoom invite. And after class, I'll replace this link with a link to the video on YouTube. So I'm using Zoom to record this meeting. And when the meeting's over with, later today, I'll copy the recorded video up to YouTube, and this will change to a link to the recorded video. Okay, so if you want to review what we talk about, if you want to check, look at it, or if you should miss the lecture and you want to see it, this each day, this will be the link to the Zoom meeting before class, and then after class, this will change to a link to the video itself. And whenever there's a new homework assignment, I'll announce it on here. Whenever on the day when a homework assignment is available, I'll put a link to it. There'll be I'll list reading assignments here. Like here's a reading assignment about data structures. Okay, and it's an online book that's it's a nice Java textbook that's online, and this is the website of the book. It's kind of a nice Java textbook that was written by a professor, and he made the whole book available online. The book is actually an introductory book on Java, but it has a little bit about data structure. So it's kind of a book that starts with the basics of Java. It starts, assuming no one's done any programming. So it starts from the basics and goes up to a pretty good introduction to data structures. If you're looking for something that you can review data structures, these chapters 9, we're going to be looking at this chapter here on linked data structures, lists, trees, and recursion. Okay, so I'm going to give you some readings from this chapter here on, well, we're not going to talk about linked lists. That's what you're supposed to have done in the data structures class. But we're going to be talking about trees. That's what this is what usually doesn't get covered in the data structures class. Usually the data structures class gets up to at least linked lists. Sometimes it depends. You may have talked about trees in your data structures class, or maybe you didn't, but I think we should review it because not everyone, I'm sure, has seen the tree data structure. And we're going to need it a lot in this class. So we're going to talk about trees, okay? And also we'll talk a little bit about recursion, okay? So the first reading assignment over here is, the first reading assignment is to this stuff about trees that we'll talk about today. Then, for example, here's a link to a zip file with some code that we're going to look at today. So we're going to look at some example code that talks about that works with trees. So we'll Java code. So this will be a zip file of Java code. We'll download it in a little while and look at it. And then I put a reading assignment from the textbook here, but we won't get to it for a while. If you have the book, you can look at chapters 1 and 2, and you'll see the connection between trees and what programming languages. So we're going to start off with talking about trees, but then we're going to switch to talk about programming languages. Like here's a summary of chapter 2 from the textbook. This is just a summary. But if you scroll down here, you see trees. See, trees play a really important part in the study of programming languages. So we're going to see lots of trees as we go along. So we're going to spend some time talking about the tree data structure before we start talking about the first couple chapters of the programming languages textbook. So chapter 2 of the programming language textbook is when trees start being introduced. But it's a programming language textbook. It doesn't talk about the tree data structure much at all. It presupposes you've seen that in a data structures course. So we'll review trees for a week or so before we jump into the use of them in programming languages in this chapter 2. The chapter 1 reading of the textbook is just an overview of programming languages. It's just it's an interesting chapter. It's not. We're not going to talk about it in class. When you get the book, you might find chapter 1 interesting. It's just kind of like a little overview and a little bit of history of programming languages in general. The real content of the book starts with chapter 2. But like I said a minute ago, it helps to review trees ahead of time. So we're going to do trees for a little while before we jump into chapter 2 of the textbook. Okay. And your first programming assignment, when it's available, is a programming assignment about trees. It's going to be a programming assignment where you're going to write some code working with the tree data structure. Okay. All right. Now let's see. So before we go on, does anybody have any question about the syllabus? Oh, we're going to meet probably the whole semester this way using Zoom. So this is going to be a class that meets every Tuesday and Thursday with Zoom. And the class will almost always be like this. I'll just show you my desktop, and I'm going to use my desktop for writing code, compiling code, and running code, and drawing pictures and showing you stuff. So I won't see your faces and things like that. So if you have questions, the fastest, the easiest way to ask me a question during class is just to interrupt me. I don't see you raising your hand or anything like that because I'm concentrating on my computer screen and the keyboard. Like if you ask a question on the chat, I may not notice it for a while because the chat's on a different monitor. It's off to the side of my desk. So in class, if you have a question, please just interrupt me. Anytime if you're not sure what I'm saying, or if you think I may not explain something very well, or you're just not sure of something, please interrupt. So like right now, does anybody have any question about the course syllabus or about the structure of the class? Anybody have any questions so far?
I have a question. Is there going to be any use for Windows at all?
I'm not sure what you mean.
Like, will we have any assignments that are Windows-based only?
No, they're Java programming assignments. Is that what you mean? Because Java is a platform.
Yeah,
neutral. Yeah. I mean, if you're working on Linux or a Mac, it's not going to make a difference.
Okay, that was basically my question.
Yeah, the homework assignments will be using Java, and later on we're going to use a couple other programming languages, ML and maybe Haskell, but they're all platform independent. Okay, so there won't be any Windows programming in this class. The operating systems class is very different because it's an operating systems class and it's very dependent on the operating systems. This class, that's one of the beauties of using Java. It's pretty platform neutral. So there won't be anything in the class that really depends on you using the Windows operating system. Okay. So we're going to use Java, and then we're going to switch to a language called ML. And then after ML, we may switch to a language called Haskell. I haven't decided what language we might follow up ML with. Okay. So I want part of the point of this class is to get you to realize the breadth of the different kinds of programming languages that are out there. So we're going to make use of some unusual programming languages. So we're going to learn a functional programming language called ML that's in this textbook. This textbook does a nice job of introducing the ML programming language. ML here doesn't stand for machine learning. This is it's an older language. ML stands for meta language. So it's kind of confusing because ML nowadays almost always means machine learning. but there's a famous programming language called the ML language, and ML actually stands for meta language. And that's the language we're going to do a bunch of programming in after we do some stuff with trees. We'll switch to the ML programming language and do some programming in the ML language. And again, that language is available for Linux, Windows, Macs, and all that. What about any other question about the course in general? Anybody got a question about the course? Okay. Okay. So let me what we want to do is start talking about the tree data structure. Okay. Now in the data structures class, let me switch to something I can draw a picture with. Okay. In data structures class, you should have talked about linked lists. So a linked list is, when you have something like this, you have these nodes, and each node is divided into two parts. Yeah. And one part of the node is a pointer, an arrow pointing to the next node. And the other part of a node is an arrow pointing to a piece of data. So each node holds a piece of data. So this would be a data object here. Okay. And then there'd be a data object here and a data object here. Yeah, so this is the idea of a linked list. Okay. You have these nodes, and the nodes point to data objects. So this is a node object, and this is some kind of, depending on what you're storing in the list, this is some kind of data object. Okay. So this is what we mean by a linked list. Okay. And at some point, the linked list comes to an end. Oops. Let's see. Let me finish this picture. There's there's a data object here, and this thing points to, now, in C or C++, these guys are pointers. In Java, these things are reference variables. They refer to an object. Okay. Okay. So we'll draw pictures of these in Java in a little while. More detailed pictures using Java in a little while. But at some point, you get to the end of the list. Like in this case, this list has 1, 2, 3, 4 things in the list. And this one will then hold a null reference to denote the fact that that's the end of the list. So there's a list of 4 items. Okay. Right. So this is the basic idea of what we call a linked list. Okay. And usually you have another reference variable over here. Oops. There'll be some reference variable over here that is a list reference variable, for example, that points to the head node, that points to this node here. Okay, so you'd have some variable that pointed to the head node, and then the head node would point to the second node, and they would point to the third node. Okay, so that's a linked list. In this textbook that's introducing the data structure stuff, okay, if you look at the chapter here, the chapter is called Linked Data Structures. And there's 2 famous linked data structures, linked list, and what we're going to see now, trees. The other kind of linked data structure is a tree. Now, most of the time, our data structures class, CS275, covers the list, usually doesn't get to tree. Did anybody cover trees? I'm curious. Did anybody cover trees in the data structures class?
No.
Yeah, usually you don't get that far. Did anybody cover it? You didn't do trees, did you? Usually we don't get to the tree data structures in the class. So that's why we're going to start off with talking about it. It's what comes right after linked list, but usually that's as far as we get in the course. We get to the linked list stuff, and we usually don't get past that. And well, we usually get up to the stacks and queues. Once you have linked lists, you can form special versions of linked lists called stacks and queues. Okay, and that's, I know when I teach the data structure class, usually that's where we end with stacks and queues. And if you look in most data structures books, you'll see that after linked lists, stacks, and queues, you often have this section on trees. Okay, so that's what we're going to start with. So a tree, now let's see, what's a tree look like? Okay, so let me save this picture. Oh, okay, now here's the idea of a tree is that when you have these nodes, the nodes would be just a little bit different. You'd have a node, but the node now would be divided into 3 parts. Okay, one part, so this would be a node. Now this is going to be a tree node. Well, in the case, it's going to be a binary tree node. So right now we're talking about binary tree nodes. So it's, instead of having 2 things in each node, there's 3 links, there's 3 reference variables. Okay, one of the reference variables will point to like before, a piece of data. So this will be a data object, some kind of data object, and this will point to the data object. And then there'll be what we call the left and right branches of the tree node. So then there'll be 2 more tree nodes here. Here's a tree node, and here's another tree node. Okay, so each one will have its 3 pieces. And what happens now, there'll be 2 links coming out of here. There'll be a link out of here to this one, and a link out of here to this one. Okay, and these are 2 more tree nodes. So this is another binary tree node, and this one's another binary tree node. Okay, it's not much, it's very similar to the idea of a linked list. It's just that each node points to what, right now it's just going to point to 2 other nodes. Later on, it could point to more than 2 nodes, but right now we're going to do binary trees because we're doing something that if I drew another kind of picture, it would look something like this. Here's the root of a tree, and then here's 2 branches below it. And what I'm doing is building a tree that would look like this. There's a tree. That's what we mean by a tree. Something, this is called the root of the tree. That's this node. And this is the left child of the tree. That's this one. And this one here is the right child of the tree. That's this one. And if the tree was really like this, then over here, I would have null in here, null in here. So this is a simple tree with 2 levels. We call this level 0 and level 1. So the tree has 2 levels. Okay, and there's null there. So this would be a pretty short tree. Okay, this node represents the root. What we call this the root of the tree. Notice that the root's at the top. Now, usually when you have trees branch. Real trees in the real world branch upwards. Trees in data structures classes branch downwards. So the root is at the top and the tree branches downwards. Okay, and then later on, the tree could get more elaborate. So for example, I could have this one having a left child, what we call a left child and a right child. Okay, and I could have another left child. Sorry, there's a left child and a right child for this one. Okay, So trees don't have to be symmetric. Okay, so here's an example of a little bit more elaborate tree. There's the root of the tree, level 0, level 1, level 2, level 3. So this is a tree with 4 levels. They're levels 0, 1, 2, and 3. So we say the height of this tree is 3. This is a tree of height 3. Okay. This root has a left child and a right child. This child doesn't have any children of its own. This child of the root has a left child and a right child. And this node has each one of these are called nodes. Just like here, they're represented, but this is how we usually draw a picture of a tree, and this is how we would actually code it in memory. A node is a little data structure with 3 links, a link to the data and a link to the left child and the right child. Over here, the data would usually just be written in, well, a lot of times when people draw pictures of trees, they'll just draw the data as like maybe this thing holds the number, say 3, and this one holds the number 4. Maybe the data is a number. So there's maybe some number. Okay, so maybe the data here is just some number. Okay. Of course, over here, there should be a piece of data for this node to point at. And the way I've drawn it here, the right child is holding 7. Okay. And there also should be another piece of data for this one. So this will point to that data node. And that one's holding, according to this picture, the left child holds 4. Okay. All right. So this is the way we'll usually draw trees on a piece of paper. And this is the way we think of it as in memory. So this, on the left side of this picture, you're supposed to think of this as the Java heap. So this is where these are all Java objects. That's an object holding 3 reference variables. That's an object that holds the data for this node. This is a reference variable pointing to another object in memory. These objects have type binary tree node. This has type, it could be int, it could be string, it could be anything. You know, we could have a tree of different kinds of data. Here I made it look like a tree of integers. When people draw pictures of trees, they often put the data just inside the node. They just, for simple examples, a lot of times you just think of the data sitting in, that's why I draw circles for the nodes. Because a lot of times in books, they'll think of the data as sitting inside of that node. Okay, so we've got this visual representation of tree, and we have the way it's laid out in computer memory. Okay, now later on we'll do slightly, let's see, let me save this. In a little while, we're going to do trees that are arbitrary trees. So you could have a tree that looks kind of like this. Here's a root, and maybe it's got 3 children. Okay. Oops. And maybe this one has 1 root, 1 child. This one will have, say, 2 children. And I'll give this one a bunch of children. Okay, so here's a tree. It's not a binary tree. We just kind of call these arbitrary trees. See, this one's got 3 children. This one's got 1 child. This one's got 2 child. This one will have 1, 2, 3, 4 children. Okay, so that's we think of this as an arbitrary tree. Every node has a different number of children nodes. Okay, and later on, this is the kind of tree we eventually want to work with. Trees where every node can have a different number of children nodes, as opposed to a binary tree, every node has exactly 2 children. Okay, In an arbitrary tree, you know, each node can have a different number of children. We say that this node has degree 3, this node has degree 1, this node has degree 2, and this node has degree 4. These nodes down here are called leaf nodes, and they have degree 0. So the bottom of the tree are called leaf nodes, and leaf nodes have degree 0 because they have no children. And I could put, say, down here, I'll put another 2 children for, say, that one. So this one's got 2 children, okay? Notice that this leaf node, this, and this, and this leaf node are at level 0, 1, 2, but these 2 leaf nodes are at level 3. So the leaf nodes don't all have to be the same level. In fact, I could put one more child down here and give him that child, okay? All right, so now this tree, this is level 0, level 1, level 2, level 3, level 4. That leaf node's at level 4, that leaf node's at level 3, these other leaf nodes are at level 2, okay? Okay, so this is an arbitrary tree. And eventually we'll look at how you would do this in Java, like how this is a little bit more complicated to do than the binary tree. So we start with the binary tree is like the natural thing after a linked list. In a linked list, each node links to 1 item. In a binary tree, each node links to 2 items. In an arbitrary tree, each node links to an arbitrary number of items. And then that becomes a question like how do you structure that? Because you could have a node with 100 children. So you could have a node that has 100 children, whereas another node has no children. So you need something a little bit more elaborate to do this kind of special case. Okay, so we're going to go from linked lists to binary trees to eventually arbitrary trees like this. Okay, all right. So these are, you know, all of this falls under the idea of a linked data structure. When you draw a picture like this, you don't think of it as being linked, but okay, let's save that. Yeah, remember, we're going to go back. We're going to constantly be going back and forth between the pictorial view of trees and the data structure idea of a tree. Now, let me go back to the course. Oops. Remember, I showed you that if you go to this chapter 2 link from the textbook, see, there's an example of a tree. Okay. Now notice that, you know, in this tree, there's the root. The root has degree 3. There's 3 children to that, but this one has 1 child that has degree 1. These 2 have degree 2. This one has degree 2. So this is not a binary tree. This is an arbitrary tree. The nodes store symbols. We'll see what this stuff means, but these nodes are storing symbols. Okay, and this tree describes the structure of a sentence. You know, actually, like here, S stands for sentence, NP stands for noun phrase, V stands for verb, NP stands for noun phrase, adjective, noun. And we'll see what this is a tree where the nodes store a symbol that represents what the tree nodes represent, and the leaves are strings. Okay, so but this is an example of a this is what's called a parse tree. Okay, so this is the way we draw pictorial representations of trees. So that's like this. But then somehow this tree is going to get represented by Java in memory as some kind of data structure. And we're going to be going back and forth between representing a tree as a data structure and representing the tree pictorially. Normally, when you're talking about trees, you like to draw pictures like this that give you a more of an abstract representation of a tree. The only time you actually worry about the way it's laid out in memory is when you're writing the code. Okay, so when you're designing the code, you have to think about this kind of picture over here. Most of the time, like in textbooks, you'll see pictures like this and like this that just represent sort of an abstract tree. Here's another one. This tree represents this arithmetic expression. Okay, we'll see that arithmetic expressions can be represented by a tree. Here's the root. The root's got 3 children. That this is a leaf node. That's a leaf node. This node here has got 3 children. That's a leaf node. This node here has got 3 children. This node's got 3 children. There's a leaf node, leaf node. Notice the leaf nodes are the symbols in the arithmetic expression. Okay, so we'll see how things in a programming language. Now notice that this is something out of a programming language. That's a piece of arithmetic. We're going to see that everything in a programming language can be turned into a tree. If statements, while loops, function definitions. We're going to see that every piece of every programming language is really represented by the compiler as a tree. Okay, and the same thing is we're going to see eventually. The same thing is true of web pages. When you write web pages and you program them in JavaScript, from the point of view of the JavaScript, the web page is a tree. In fact, that tree's got and you may have heard the name, it's called the document object model. When you write JavaScript code to interact with web pages, the web page becomes a tree, but the tree is given the name document object model. Okay, so we'll talk a little bit about that because it's an interesting application of what we're going to learn in this class. But to a JavaScript program, a web page looks like a tree. Now they don't show any pictures. They usually don't draw pictures of the document. Every once in a while, you'll see somebody draw a nice picture of the document object model as a tree. Yeah, here it is, like there. If you've done any web page, those are the tags in a web page: table tag, table body tag, table row tag, and the tags form a tree. Okay, so there's a graphical representation of a DOM. A DOM is a tree. Okay, so you can see trees are ubiquitous in computer science. Trees are ubiquitous in programming. They're all over the place. So like these are, see, this is the website for the people who are in charge of documenting HTML. They're called the w3.org. This is the actual documentation for the internet, for the HTML and JavaScript. And they right away, a DOM is a form of a tree. Okay. So it's real important for us to spend a little bit of time talking about tree data structures because they're just going to be so ubiquitous for us. They're going to show up in so many different ways. Like here, an arithmetic expression is a tree. I mean, here, this was doing English language. This is a sentence in the English language as a tree, what's called a parse tree. Okay, so that's one example of using a tree. That's not really, well, that's a computer science example if you're going to do natural language processing, if you're going to write code that tries to do machine learning and understand natural languages. The first step of any time of natural language processing, the first thing you do is turn English sentences into trees. They're called these parse trees. So programs that try to do translation of languages or try to understand languages, they always start by taking the language and turning it into a tree, a parse tree. So that's language as a tree. This is programming language as a tree. Over here, this is web pages as a tree. And web pages are just another example of a language. The language is HTML. So trees are going to be really important for us. Okay, and you can see here, this is that symbolic kind of picture. That's the picture that you see most often, this symbolic picture. Now, that's actually stored in computer's memory. In the case of JavaScript, that's stored as some kind of data structure. Okay, and you have to kind of, as a programmer, you have to be able to go back and forth between the symbolic representation of the tree and the actual data structure that represents the tree. But the data structure will vary depending on what language you're using. A JavaScript data structure doesn't have to look like a Java data. It'll kind of always be something like this. But then you have to turn this into something like you'll eventually want to turn this into C++ or Java or JavaScript. And that'll change the way you write the code. But the ideal looks something like this. So even this picture here on the left is still symbolic because it isn't until you turn this into actual C++ or Java or JavaScript that you know exactly what you're talking about here in memory. Okay, so I mean, this is the symbolic notion of a tree. This is sort of a semi-symbolic idea of how the tree is structured as a data structure. And then there's the real concrete write code. That's what we'll turn to in a little while. In a few minutes, we'll turn to real code that draws a tree using the Java programming language. Okay? Okay, so trees are important. You know, they're just everywhere in programming languages. Okay, and if you go to this reference here, here's a section on arithmetic as they're called expression trees. When you take arithmetic expressions and you draw them as trees, they're called expression trees. So that's a good example that's going to be important to us as we go along. That's one use of a tree to represent arithmetic expressions, and those are called expression trees. Okay, and there's a bunch of other like here we're going to in this reading assignment, I told you to read sections 9.41 and 9.43, expression trees. In between, you can read this if you want. This is another way that people use trees, but we're not going to do it in this class. Trees are used to do sorting. There's something called a binary sort tree. Databases do this a lot. When you need to keep things in a certain order, if you need to keep things in an order, trees actually you'd think keep things in an order using a linked list. You know, a linked list has a first, second, third, fourth, fifth things. But it turns out that when you need to keep things in order, a lot of times a tree is actually a more convenient way. So there are sorting trees. Okay, so this is we're not going to need this in this course. So the reading assignments for you to read section 9.41 about tree traversal and 9.43 about expression trees, because those are the ones we're going to be using. And if you want, you can read the middle section because it's interesting, but it's an example of using trees that we don't need in this class, but it's a real ubiquitous use of trees to store data in a certain order, what are called sort trees. Okay, so trees come up in programming in lots of ways. If you look at an advanced course on data structures and algorithms, you'll see lots of uses of trees that are beyond what we're going to need in this class that do go into all kinds of a lot of machine learning algorithms are tree based. There's something called decision trees. There's a famous machine learning algorithm called decision trees that uses trees to help artificial intelligence programs make decisions. Okay, so the tree data structure is a basic data structure that gets used in a lot of ways. We're going to use it for programming languages. And then there's a whole bunch of other ways that people use trees also, like natural languages, decision trees in machine learning, sorting trees in databases. There's also another thing called B trees. B trees are not binary trees. B trees are another way that you implement databases. There's something called they're called B trees. Okay, it stands for balancing tree, and they form the basis for this building databases like Oracle and SQL, MySQL. The underneath a database system is something called a B tree. Okay, so that's another example of a use of a tree. Okay, so we're gonna mostly be working. The tree that we're gonna work with the most is this one, the expression tree. This is actually the key example for us. In terms of working with programming languages, this is the kind of tree that we use the most. And later on, we'll change the name of it from expression tree to what's called abstract syntax tree. So we'll generalize expression tree to something called abstract syntax tree, and that's what we'll work with a lot in this class. Okay, so this is our main example of a tree. And if you're interested in machine learning and databases, this example would probably be more important to you, the sorting trees. That's more of leading into the direction of using trees to store data in databases, or using trees to understand data, like in machine learning or data sciences. Okay, right? Okay, now let's go back to the, okay, over here. I'm going to download this zip file with some code that lets us start programming trees. Okay, so I'm going to download the zip file and unzip it. And like I said before, if you have questions, just interrupt me. If there's anything you're not sure about, if I seem to, especially if I say something funny and it doesn't make sense, I may have, if you think I maybe said something wrong, just ask. Okay, so here's a bunch of code that implements binary trees. Okay, so let's start with this class right here. That's the class that describes one node of a tree. Okay, so that's going to be the Java class that describes one of these nodes. See, a node holds three things. Okay, so let's look at this code. Okay, a B tree node holds three things. Okay, in this case, it holds a reference to a string. So I'm going to be, in this picture here, I'm going to be treating these as strings. Okay, so this is going to be a string piece of data. So the a B tree node holds a reference to a string, then it holds a reference to another tree, and I call it left. It holds a reference to another tree that I call right. Okay, that's these two references here. A reference to the left binary tree node and a reference to the right binary tree node. Okay, so I called the nodes B tree. Okay, so I just, so B tree and a B tree. Notice that there's a recursion here. What's a B tree? A B tree is two more B trees. Okay, there's an inherent recursion here that the definition of a tree uses a tree. Okay, and in this folder here, there's something called the B tree language. Okay, this is where what we're talking about here blurs into the textbook of the course. This is a description of a tree in what we call a grammar. And this is actually, we're gonna have to come back to this because this is what chapter 2 is about in the actual course textbook. This is what the chapter 2 is about what we call grammars. So this is the grammar for a tree. Over here is the code for a tree. This is the Java code for a tree, and this is the grammar for a tree. And the grammar of a tree says that a tree is a string and another tree and another tree. Or, now, we're going to allow the left branch to be empty, and we're going to allow the right branch to be empty. So we're going to allow, in our code, we're going to actually change it a little bit. Instead of a binary tree like I drew here, always having every node having a left and a right node, I'm going to also allow trees to have a right node but no left node, or have a left but no right branch. So we're going to allow trees to be funny where not everybody does it this way. In some people's code, a binary tree either has, it's like this picture, either you have a leaf node with no children, or you have a node with exactly two children. And some people allow their binary trees to be a little bit more general. A node can have either one or two or no children. Like a leaf node has no children. You're allowed to have a node that can have either one or two children. Over here, I wrote it so that, well, over here, I described this as saying that a tree can have two children, or one child on the right, but no child on the left, or one child on the left and no child on the right. Or a tree can be just a node by itself. See, so it can be, notice that I do not say string empty empty when you have a, this is the case of a leaf node. So this is where the leaf node is. The leaf node is just a string. Okay, right? So this is the grammar. No, this is the here. This is a recursive grammar. A tree is defined in terms of trees. Okay, and if you think about the picture we drew over here, if you kind of cover up this part, like if you, I don't know if I can see, if you kind of cover up part of the picture, see, can I cover up? Oh, I know what to do. There, see, okay. See, I'm going to use this guy to cover up. See, I covered up part of the picture. That's a tree. Or if I cover up this part of the picture, there's a tree. See, a tree is made up of trees. Yeah, that's the recursive way of thinking about this. If you cover up most of a tree, what's left is a tree itself. Okay, so see, so I cover up that. That's a tree, but that tree is the left child of this tree. So that's the recursiveness of it. That a tree is made up of trees. This tree, so this tree here, see this big tree that's rooted at 3 has this smaller tree rooted at 4. And then if I get it, let's see, if I pop up another window, can I pop up another see, if I cover up a little bit more, you see another tree. See? That tree was part of that tree there is the tree that's making up the right branch of the tree rooted at 4. And the tree rooted at 4 is the left branch of the tree rooted at 3. So a tree is naturally recursive. A tree is made up of trees. Or if you use this other grammar, a tree is made up of trees. Okay? Okay. So we call these sometimes recursive data structures. Remember the textbook referred to them as, this is kind of an interesting way to think about it. If you go back to the textbook here, this chapter was called linked data structures and recursion. In a lot of textbooks, this section is called recursive data structures. Instead of calling them linked data structures, it's quite often in a data structures textbook for this section to be just called recursive data structures. Because a linked list and a tree both, what's a linked list? If you go back to our picture of a linked list, it's also recursive. Because if you take this list and you cover up the beginning of it, there's a list. And if you cover up that part of it, you're left with a list. So a list is made up of lists. Okay. A list is really what a list is an item with a list after it. And that list is an item with another list after it. So lists are also an example of a recursive data structure because a list is made up of sublists and a tree is made up of subtrees. So some people refer to them as linked data structures, but a lot of people actually refer to them as recursive data structures because when you go write the code for them, so when you actually go write the code, you get this recursiveness of the definition of a tree involves a tree. Okay? You know, it's self-referential. What's a B tree? Well, a B tree is a B tree. Yeah, actually, this is not trivial. The in English language, if somebody asks you what the meaning of a word is, you can't use that word to define the word. Then people just tell you have a circular definition. So how does a programming language work where the definition of a B tree is, well, yeah, think of it. What's a B tree? Well, I have to know what a B tree is to tell you what a B tree is. There's inherent quirkiness to this. It's actually kind of subtle. How can you tell me what a B tree is if you have to know what a B tree is to build a B tree? Okay. And the way this is resolved is, this is just a reference to a B tree. So it's really not a B tree. There's a subtle difference here. This is what a B tree is, but this is really not a B tree. It's a reference to a B tree. And that actually resolves what seems to be a paradox. This guy here and this guy here are not quite really the same thing. Okay, this is the B tree data type. This is a reference to a B tree object. So I'm not, and that's a subtlety of the way the language is designed. Okay, here, see, class B tree. So this guy's defining a class. But this is not a class. This is a private variable. It's a field. So this is a reference variable. It's a reference variable of that type, but it's not, see, it's not the same thing. This is defining a class. This is defining a reference variable. They just happen to have the same name, but they're slightly different things. So there's really not a paradox here of I'm defining something for you using the thing I'm defining. So I don't have a circular definition here, but it's very subtle that there's this slight change from this word meaning the definition of a class and this word here meaning the type of a reference variable. Okay, and what that amounts to is over here, if I go back to the picture, see, this is the B tree node. That's this guy here. This box is a pointer to another B tree node. That's this guy here. Notice that the B tree node is not sitting inside of there. See, now suppose you did what, suppose you tried to put this guy inside of there. That wouldn't make sense. That, it can't be, tell me what, suppose I told you that, let me draw a picture here. Here's what really wouldn't make sense. Suppose I told you that a B tree node held data, and it had inside of it, now here I'm going to say inside of the B tree node is another B tree node and another B tree node. Okay, this picture doesn't make sense. This picture is very different than this picture over here. Can anybody see what's kind of wrong with this picture? I'm claiming that a B tree node holds three things: a piece of data, a B tree node, and a B tree node. This
circular logic.
Pardon me?
Like circular logic.
Well, where is it? Where now? Why was, see? I claimed that over here there isn't a circular logic, but over here there is. Where is the circular logic in the right-hand picture that's not there in the left-hand picture?
The B tree nodes are actual data types, not references.
Right. So what's inside of this box here?
Another 2 more B tree nodes.
Right. And what's inside of those?
2 more.
And what's inside of those?
2 more.
Where does this end?
Never.
Never. Yeah, because my definition, this is truly recursive with no end to the recursion. A B tree node holds a B tree node. Then the B tree node would hold, then I don't know if I can find it on the internet. There's some really nice videos of this kind of recursion. Let's see if I can. There's one particular video that somebody created once that's a really great example of recursion. I can't remember where it is. Oh, there it is. I found it. See, the briefcase holds a copy of the picture of scene, which holds a copy of the scene, and it just kind of keeps going forever. Okay, it's a clever kind of representation of the paradox that's in this picture here. What's inside of a B tree is a B tree node. What's inside the B tree node is another B tree node. What's inside the B tree node is another B tree node. That would go on forever. That's what you don't do in a Java programming language. You can't program this. It doesn't make sense. The reason we don't have, what we do instead is we say that a B tree node holds a reference to another B tree node. The other B tree node is not inside of there, it's out here. Now in the code, that's done in a very subtle way by saying that the B tree class, an object of type B3, holds references to objects of type B3. So this and this are not quite the same thing. It's the difference between this picture and this picture. You know, if this B tree was literally this B tree, it'd be this picture here. A B tree holds a B tree, which holds a B tree, which holds a B tree, and that would go on forever. Okay, but instead it's this picture here, where a B tree object holds a B tree reference to another B tree object. So the thing that's over here is not really inside of there, it's really outside. It makes all the difference in the world. By doing it this way, there's nothing it's not infinitely recursive. It's not a circular definition. But if you did it this way, it would be. No programming language would let you do this, because if you try to do this in a programming language, you'd fill up memory, and this would start filling up memory, and you would run out of memory. This doesn't make sense. Okay, so all programming languages, when you do these recursive definitions, there's actually something very subtle going on. Now, if you did this in C++, it wouldn't look so recursive, because in C++ you'd put a little star here to say that this is a pointer to a B tree. And you put a star there to say that it's a pointer to a B tree. So then it would become, say, oh, a B tree holds a pointer to a B tree. So it doesn't hold the same thing. So in C++, it's even a little bit clearer that it's not quite self-referential. Because in C++, you'd say that a B tree holds a pointer to a B tree. But in Java, you don't use the pointer symbol. You just do it like this. And it kind of looks self-referential, but it's not, because this is the B tree class, and that's a B tree reference variable. So the picture is this one, not this one. Okay? Okay, so it's kind of a subtle thing. If you could, there's, by pointing over to here, there's nothing you don't have something inside of something inside of something inside of something. You have something just pointing to something else, and then that something can point to something else. Whereas here you'd get this weird, you would get the true recursion of this thing holds a copy of itself. So then you get that video. See, then you would be in this video kind of situation where each item holds a copy of itself, and you'd have to open that up, and then you'd have to open the next one up, then you'd have to open the next one up, and you'd have the next one up forever. Okay. I think this video is really neat. It does a good job of kind of, I don't know why they thought to make it a video of, you know, somebody opening a briefcase in front of an inspector, but it captures the idea perfectly of what would be wrong with this picture over here. Why you can't have a node holding a node. You really have to have a node holding a reference to a node. Okay. Okay. So that's the idea that we need to cover. Yeah. So that's where, like I said, instead of calling these linked data structures, which is what they really are, some people like to abstractly refer to them as recursive data structures, but then you have to be careful. It's not this picture, it's still this picture. It really does mean linked. But see, he called it linked data structures and recursion. Okay, so that's, you know, that's not a bad point. They're linked data structures. The data structure points to another data structure, a copy of its. So, you know, one node points to another node, but it's meant to represent a kind of recursion. And when you write code that works with these trees, you write recursive functions. Okay, we'll see that what we're going to do is we write recursive functions to work on these linked recursive data structures. So we're going to make quite a bit of use of recursively written functions to work with this recursively defined data. Okay, but the data is not really recursive. It's really more, it's linked. So the linking is really kind of representing this idea over here. Okay, very subtle ideas. Recursion, a lot of people think of recursion as this really abstract, super complicated idea in computer science, and that's really bad. People should never be afraid of recursion. Recursion lies at the heart of everything that computer science does. I mean, I showed you how, like, the DOM in HTML is a tree data structure, and a tree data structure is a recursive data structure. You know, recursion exists everywhere in computer science. Somehow trying to pretend that you can avoid it is very wrong, because if you try to avoid the recursion, you're just sticking your head in the sand, and you're trying to avoid something that's it's everywhere, and it's hard. I mean, you know, facing the recursion and dealing with it directly is tricky, but it's wrong to try to avoid it and pretend that it's not there. I read all kinds of stupid stuff on the internet where people say you should never write recursive functions, or you should avoid recursion, or that recursion is just people trying to show off, and that's just really nonsense. You know, no real sophisticated code can be written without recursion. Almost all the really sophisticated code out there, compilers, interpreters, machine learning systems, they're all written using recursion all over the place, because recursion is so important to computer science because of these data structures, especially because of the list and the tree. The list and the tree data structure are linked recursive data structures. And since those data structures are everywhere, that means that recursion is really everywhere. And the best way to process a linked list, or the best way to process a tree, is to write recursive functions. And we'll see that pretty soon. Okay, all right, so we've got this Java code. Okay, see, so a tree is a reference to data and two more branches. Okay, and then here's the constructor. So if you give the constructor, well, if you give the constructor just element, then it sets the left and right reference variables to null. This represents a leaf node. See, this constructor builds a leaf node with no children. This constructor builds a node with a left and a right child. So we have two constructors, one constructor that builds a leaf node, and one constructor that builds what we call an internal node, a node with a left and a right child. But if you make this thing null, then you only have a right child and not a left child. And if you make this thing null, then you have a left child but no right child. And if you make both of these null, then it's redundant with this constructor. So there's a little bit of redundancy here. If you make this one null and this one null, you got really the same thing. You're creating a leaf node. So it's the same as this one. Okay. Then there's a get element. you can get the left tree, you can get the right tree, you can replace the left tree, you can replace the right tree. Okay, so there's a bunch of little bookkeeping methods. Get a reference to the data, get a reference to the left tree, get a reference to the right tree, replace the left tree, replace the right tree. Okay. Now here's where we start getting into okay, this one, each node in the tree has a different number of children. So in the case of a binary tree, a node can have either 0 children, 1 children, or 2 children. Okay, so that's called the degree of the tree. Okay, remember we said a degree is how many children a node has. So you call this method on a node and it counts how many children there are. So by default, it says, okay, the result is 0. If the left node is not 0, you count 1 child. If the right node is not null, you count the other child. So results can either be 0, 1, or 2. Okay, that's the degree of a node. Okay, now here's where things get interesting. What's the depth of a node? The depth is how many levels are there below you. Okay, so if we look at one of our pictures, the depth of a tree asks how many levels are there below you. So this tree here has depth 1, 2, 3, 4. Okay, but this node has depth 1. There's only 1 level below it. A leaf node has depth 0, has nothing below it. Okay, now think about this node here. What is his depth? His depth is 1 more than the maximum depth of this guy, and this guy. Okay, this is the recursive this. The depth of this guy is 1 more than the maximum depth of this guy, or this guy. Depth is recursive. Because see, okay, what's the depth of this guy? This guy's depth 1, this guy's depth 1, this guy's depth 1, 2, 3. So what's this guy? This guy's depth 1 more than this guy. It's depth 4. 1 plus this is depth 1, depth 1, depth 3. So then this one is 1 more than 3, which is 4. What's the depth of this guy here? He's 1 more than the depth of this guy, which is 0, the depth of this guy, which is 0, the depth of this guy, which is 0, and he's 1 more than the depth of this guy. But the depth of this guy is 2. Oh, where'd that do? I don't know what that was. Okay, so depth is, now look over here. How do I program that? In words, the depth of a tree, the depth of a node is 1 more than the maximum depth of all its children. Okay, so what do I do here? The result is going to be the depth of this node. Then I have a variable, the depth of the left child, the depth of the right child. If there is a left child, recursively ask for its depth. There's the recursion. See, depth is defined in terms of depth. See, the depth method is defined in terms of the depth method. There's the recursion. If I want to know the depth of this node, I say, well, if he's got a left child, ask for the depth of the left child. If he's got a right child, ask for the depth of the right child. Figure out which one of those is the maximum and add 1 to it. Okay? Okay? Okay. So actually, see here, I already put there's the 1 that's going to get added to the depth of the left or the right child. Okay? So there's the recursion. Okay? Notice that this is going to be ubiquitous. Whenever you process a tree, you process a tree by doing some sort of recursion. If I want to know something about this tree, the answer has got to do with this subtree, and this subtree. One last example, we won't finish it, but the size of a tree counts how many nodes there are. Like this tree has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The size of this tree is 14 nodes. Okay? What's the size of this tree? The size of this whole tree is 1 plus the size of this tree, plus the size of this tree, plus the size of that tree. See, the recursion. The size of this tree is 1 for that node, plus size of this guy, size of that guy, size of that guy. Okay, so over here, size, well, you need the size of the left tree and the size of the right tree, and you add them up together. Okay, recursion. Okay, all right, so we ran out of time. It's 1:45, so we're going to quit here. And we started to see how, you know, working with trees, the tree is a recursive data structure, and when you work with trees, you write recursive functions. So we've got a recursive function for depth and a recursive function for size, and we'll write some other recursive functions later on. Okay, all right, so that's the kind of thing that we're going to be doing. So at this point, we should quit. Okay. Oh, if you, I probably should make it a reading assignment. This section 1 is about recursion. You might want to read that too. I think I should make that a reading assignment. So there's a little bit of a review of recursion here in this section here. Okay. So you know, and also if you have your data structures book from last semester, the 275, there's a good chapter on recursion in the data structures book. So if you've kept your data structures book, look up the chapter on recursion in there. It's a good explanation of recursion also in there. And also trees are in there. If you have your data structures book, a good reference for trees is your data. If you've kept a copy of it, or if if you can find a copy online, the data structures book does a good job of describing trees also. Okay, so now on Wednesday we didn't get to the homework assignment's not up there. On Wednesday we'll continue talking about this stuff on binary trees, and we'll see how the first homework assignment is going to be a homework assignment where you write some code using you have to write some code where you do some write some recursive functions on binary trees. Okay, and anybody got any last minute question before we quit? Any last minute question? Anything else? Okay, so oh, you have to, I leave it up to you to put Java on your computer and stuff like that. Since this is a more advanced class, I'm not, the programming language for the class is Java. I'm going to leave it up to you if you want to, whatever version of Java you want to use. So, if you don't have Java on your computer and you need help with that, let me, come to office hours or send me an email. If you don't happen to have Java on your machine and you need help putting it on there, let me know. But you do need to get a copy of Java and put it on your machine. So you can compile and run this code that is in this folder. Okay, all right, so I'll go ahead and I'm going to stop the sharing, and then I'll end the class. If you have questions, send me an email. I have office hours on Tuesday and Thursday afternoon, so the office hours actually in about an hour from now. I'll start office hour. If you have questions, you can come to office hour, or you can send me an email. Okay, so see you again on Thursday then. Okay, bye.